Our universe is full of wonders. Some are hidden in plain sight. Porous media, materials filled with intricate networks of pores, are one such marvel. Think of a sponge, soil, or even the human lung. These materials, with their hidden pathways, play a crucial role in countless natural and industrial processes. Heat transfer, the flow of thermal energy, takes on a new dimension in porous media. It's a dance of conduction, convection, and radiation, all happening within these tiny spaces. This intricate dance affects everything from the efficiency of fuel cells to the safety of nuclear reactors. Imagine a catalytic converter in your car. It's a porous media marvel. Exhaust gases flow through its intricate channels. Heat transfer is key to converting harmful pollutants into harmless substances. This process is essential for a cleaner environment. The world of porous media is vast and complex. Understanding heat transfer within these materials unlocks a universe of possibilities. From energy to healthcare, the applications are endless. Let's embark on a journey to unravel the mysteries of this hidden world. Porosity, the measure of empty spaces within a material, is the heart of our story. It dictates how fluids move and heat flows. Imagine a crowded room. It's harder to move around, right? Similarly, higher porosity allows for easier fluid flow. This affects the rate of heat transfer, but porosity is not so simple. There's global porosity, the overall void fraction in a material. Then there's effective porosity, the measure of interconnected voids that actually contribute to fluid flow. Think of it like roads in a city. Not all roads lead to your destination. Only the connected ones matter. And then we have specific surface area. This measures the total surface area of the pores per unit volume. A higher surface area means more contact between the solid and fluid phases. This enhances heat transfer. Understanding these characteristics is crucial for accurate modeling. It's like knowing the layout of a city before you navigate it. With this knowledge, we can predict how heat will flow through a porous material. This paves the way for efficient design and optimization. The world of porous media spans vast scales, from microscopic pores to macroscopic systems. How do we bridge this gap? Enter the representative elementary volume, REV. Think of it as a zoom lens. It allows us to focus on a small representative portion of the material. The REV is large enough to capture the essential characteristics of the porous structure, yet it's small enough to be computationally manageable. It's like choosing the right map scale for your journey. Too small, and you miss the details. Too large, and it's unwieldy. The REV concept is crucial for modeling heat transfer in porous media. It allows us to simplify complex geometries. By analyzing the REV, we can predict the behavior of the entire material. This simplification is essential for practical applications. To navigate the labyrinth of porous media, we need a map. Mathematical equations provide this guidance. These equations describe how fluids flow and heat transfers within these complex structures. The continuity equation is our compass. It states that mass is conserved. What goes in must come out. This fundamental principle governs fluid flow through the porous network. Next, we have the momentum equation, our guide through the twists and turns. It describes the relationship between fluid flow, pressure, and viscous forces. It helps us understand how fluids navigate the intricate pathways of the porous material. Finally, the energy equation sheds light on the heat transfer process. It accounts for conduction, convection, and radiation within the porous medium. This equation helps us predict temperature distributions and heat fluxes. These equations form the bedrock of porous media modeling. They allow us to translate physical phenomena into a mathematical language. This language helps us understand and predict the behavior of these complex systems. Section 5102, choosing the right model for the job. In the realm of porous media modeling, we have a choice to make, one equation or two. These refer to the number of energy equations used to describe the system. The one-equation local thermal equilibrium model assumes that the fluid and solid phases are at the same temperature. This simplification is valid when the heat transfer between phases is rapid. It's like assuming the air and furniture in a room are at the same temperature, but sometimes this assumption doesn't hold true. When the heat transfer between phases is slow, we need the two-equation local thermal non-equilibrium model. This model considers separate energy equations for the fluid and solid phases. It's like acknowledging that the sun-baked sand can be much hotter than the air above it. Choosing the right model depends on the specific applications. For systems with fast heat transfer between phases, the one-equation model is sufficient. But for systems with slow heat transfer, the two-equation model provides a more accurate representation. Section 6. From theory to reality, case studies in action. Now let's bring our theoretical understanding to life. Consider the design of a fuel cell. These devices use porous electrodes to facilitate electrochemical reactions. Modeling heat transfer is crucial for optimizing their performance and durability. By using ANSYS Fluent, engineers can simulate different designs and operating conditions. They can analyze temperature distributions within the electrodes. This helps them identify potential hotspots that could degrade the fuel cell. Through simulation, they can optimize the design to ensure efficient and reliable operation. Another example is the food processing industry. Drying processes often involve heat and mass transfer in porous media. Simulating these processes can help optimize drying time, energy consumption, and product quality. Imagine a farmer drying grains. CFD simulations can help determine the optimal airflow and temperature to preserve the nutritional value of the grains. These examples highlight the power of CFD modeling in real-world applications. By accurately simulating heat transfer in porous media, we can optimize designs, improve efficiency, and develop innovative solutions. Section 7. MR-CFD, your trusted guide in porous media simulation. Navigating the complexities of porous media simulation can be daunting, but fear not, for you don't have to go it alone. MR-CFD is here to guide you. MR-CFD is a team of experienced CFD engineers specializing in porous media simulations. They provide expert consulting services, helping you tackle even the most challenging problems. Whether you need help with model setup, analysis, or interpretation, MR-CFD has you covered. Their expertise spans a wide range of industries, from energy to aerospace to biomedical. They can tailor their services to your specific needs, providing customized solutions to accelerate your research and development. With MR-CFD by your side, you can confidently navigate the world of porous media simulation. Their expertise will empower you to unlock the full potential of CFD and drive innovation in your field. Section 8. The power of prediction. Optimizing industries with CFD. In today's competitive landscape, optimization is key, and when it comes to porous media, CFD simulations provide the power of prediction. Imagine being able to test different designs and operating conditions virtually without the need for costly and time-consuming physical prototypes. CFD allows you to do just that. By simulating heat transfer in porous media, you can identify bottlenecks, optimize flow paths, and enhance overall performance. This translates to reduced costs, improved efficiency, and faster time to market. The applications are limitless. In the oil and gas industry, CFD simulations can optimize enhanced oil recovery processes. In the pharmaceutical industry, they can aid in the design of drug delivery systems. The power of prediction through CFD is transforming industries worldwide. Section 9. Beyond the horizon. Future directions and challenges. As we delve deeper into the world of porous media, new frontiers emerge. Multiphase flow, where multiple fluids coexist within the porous structure, presents exciting challenges and opportunities. Imagine modeling the flow of oil, water, and gas in an underground reservoir, or simulating the transport of nutrients and oxygen through a biological tissue. These complex scenarios require advanced modeling techniques and computational resources. Another frontier is the coupling of heat transfer with other physical phenomena such as chemical reactions or mechanical deformation. This multi-physics approach allows us to simulate even more realistic and complex systems. The journey of porous media exploration is far from over. As we continue to push the boundaries of knowledge, we can expect groundbreaking discoveries and innovations that will shape our world. Section 10. Conclusion: embracing the future of porous media exploration. We've journeyed through the hidden world of heat transfer in porous media. We've explored the fundamental concepts, the governing equations, and the power of CFD simulations. We've seen how this knowledge is applied in diverse industries, from energy to healthcare. The future of porous media exploration is bright. As we continue to unravel its mysteries, we unlock new possibilities for innovation and advancement. By embracing the power of CFD and collaborating with experts like Mr. CFD, we can navigate this exciting frontier and shape a better future. The universe of porous media awaits. Let's continue to explore its wonders and harness its potential for the betterment of humanity. Our journey has just begun.